change of solution for calcium chloride, and then also enthalpy change of hydration of a chloride gaseous atom. Okay, so let's first see what on earth is going on in here and identify a few things. So this arrow is just a bit thick and in the way at this stage. We'll bring it in now. Again, so let's talk about the first changes, that change in W in there. That change in W. Over here we go from calcium solid to my calcium ion. So we need to go through my ionization energy. So this we get from our data booklet. So this is important. My first ionization energy, that 590, and the second ionization energy, this is ionization. That's important. That comes from my data booklet. Right? Also, I needed to go from my calcium as a solid to calcium as a gas, and that's my atomization energy. That was actually given to me, my atomization. So I'm filling in on my graph, or on this, whatever it is, let's call it diagram, whatever I can. So I have that. Now calcium for that is done. My chlorine is also going through a few things. It's gas, but I need to break my molecule. So that's my atomization. Is that given? No, it's not given. I need to get that from my data booklet as well. That's my atomization that I need to get, because I need to get in chlorine gas atoms. And then I need to go through a process of electron affinity. Each one of those gaseous atoms must receive an electron. Wow. Okay, so that's for W. By the way, this is my first question. Calculate the enthalpy change corresponding to transformation W. And all of these, my atomization of calcium, my first ionization, my second ionization, are all positive values. They're going up. My atomization of chlorine is also positive. It also adds up. So positive, 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 positive. But my electron affinity is given to me, and that's negative. And that's going in the opposite direction. So I need to subtract that from it. And that gives me my answer in kilojoules per mole of 1,477. Okay, so that's my first question. It's a freaking 1 mark question. No, it's 2 marks. My goodness, at least it's 2 marks. Right, okay. Then there's some other information given to me. Enthalpy change of formation. My formation, what's my definition? From my elements in standard state to 1 mole of the substance formed. So there's my enthalpy change of formation. From solid to aqueous, this is my enthalpy change of solution. This is the next one that is given to me of calcium chloride. And then there is the enthalpy change of hydration given. Let's do this in blue. Alright, so we need to identify a few things. Remember, what is lattice energy? Lattice energy is when I go from my ions in the gaseous state to the lattice. That means in solid. So that green arrow indicates my lattice energy. My Z on this side is actually enthalpy change of hydration, because I'm going from my gaseous ions to my calcium chloride aqueous. So that's actually hydration. I got a part of it, my hydration of chloride, one of them, but to get the full hydration one, I would need to say, well, it's 2 times the negative 364 plus the enthalpy change of hydration of calcium. That's going to give me my Z. I don't think that is my second question. No? Sorry, it says use your answer in AI and all the other data to calculate the corresponding enthalpy change corresponding to Z. Okay, so I can do the rest. I can do this blue arrow that I indicated in here. I can do this whole one because that gives me the same as the other. So I can do that change in W, but negative that I just did. There it is, so negative that. I am moving in the same direction as X, so negative 795, and also in the same direction is Y, which is negative 83. And that gives me my enthalpy change of negative 2355 kilojoules per mole. That's my full enthalpy change of hydration actually now, because that's what I established with this red arrow. Last question that they ask on this is calculate the enthalpy change of hydration, and I can do that now because I know I've got the whole enthalpy change of Z. I know what the enthalpy change of hydration for each chloride gaseous ion is, and what is left is my enthalpy change of hydration for calcium. Okay, so quite a humdinger of a question for 6 marks. I'll write an expression in terms of Wx, Y, and or Z to show the enthalpy changes for the transformation for lattice energy. Luckily, we know our definitions, and we know that enthalpy change for lattice is this one. So we can say it is Z minus Y. That's going to be the easiest one. Z minus Y. Or they say X minus W is also, well, X minus W, because W is going in the opposite direction. So if we change that arrow, it becomes minus W. That's going to give me the same as my lattice energy, this one going down there. Okay, so wow, 7 marks, nice question. The bottom one most you got as well, I think. State whether the lattice energy of calcium chloride is more or less exothermic than the lattice energy of magnesium fluoride. Well, less exothermic because both ions are larger, right? Your calcium in calcium chloride is larger. Well, my chloride is larger than my fluoride, and my calcium is larger than my magnesium in there. All right. So important. Remember, go through that theory again. The names of 2 solutions that can be mixed to make barium sulfate. So we need a soluble barium and we need a soluble sulfate. Now, please remember this. I mentioned it before. So they say in the memo, soluble barium salt and a soluble sulfate. There are various options, but all nitrates are soluble. So barium nitrate, soluble. All group 1 elements in compounds are soluble. So sodium sulfate or barium nitrate. But please remember, sulfate has a -2 charge. Nitrate is a -1 charge. You need to balance those out to get to the correct formula. And then I promised you I will ask one of those solubility questions, and this one of the sulfates. The 4 points that you need to state, please. They become less soluble down the group. Think about barium sulfate. That's my test for sulfates, by the way. If I add barium nitrate to any sulfate, a white precipitate forms and I get barium sulfate, so it's insoluble. So we know that both the lattice and the high hydration enthalpies decrease down the group. That would be your 2nd mark. And then the enthalpy change of hydration decreases faster. All right. Why? Because my sulfate ion is much larger than my metal ion. So what does that mean? This means my enthalpy change of solution gets less exothermic. If it gets less exothermic, it becomes less soluble. Go and look at the theory that we dealt with and nice explanations that I gave on that worksheet as well. Right, please go have a look at it. So that was the first 13 marks on the Born-Haber cycle and enthalpy changes. Then we go into the entropy. And here you guys did really well. I have actually no problems. So just the memo again. Remember, I would like you to write the formula, please. I know the memo is very pinpoint, just giving the detail where the marks are. But if you don't have the theory and the formulas, it's very difficult to just write down anything. Just don't slap down any numbers on the page. Write formulas. Okay, so here we go again with this nice question, and again with Gibbs free energy. I told you this equation will also appear somewhere in the question. So delta G is equal to delta H minus T delta S. So Gibbs free energy equals enthalpy change minus temperature times your entropy. Now, you calculated your entropy, but it was a value in joule, so you needed to convert to kilojoule. Temperature you needed to convert to Kelvin, and now you can do the calculation. It's a positive value, that means the reaction is not feasible or not spontaneous. Again, you guys got that. Going over into my transition metals, explain what is a polydentate ligand. There's two options. It's a species that donates more than one lone pair to form dative covalent bonds to a central metal ion. But that's more or less the one that we dealt with in class. When a solution of EDTA is added to a solution of CD, what is that, cadmium? I have no idea. Probably cadmium. Okay, and 6 water surrounding, a new complex is formed. So we have this reaction. So immediately we can see EDTA will have 6 bonding points, or 6 lone pairs that it forms, 6 dative covalent bonds, however you want to say it. Right, question. Circle on the structure, the 6 atoms that form bond with the metal ion. Right, so it's my 2 nitrogens, and then those oxygens have lone pairs to share. So those are the 6 atoms that you needed to circle for the 1 mark. Okay, write an expression for the stability constant. Remember, stability constant, products over reactants, but we do not take liquid water into consideration. Alright, that's not in there. 2 marks, 1 for the formula and 1 for the unit. You guys can do that. My B is a slightly different question to what you guys are used to, but just bear with me. They say we have 2 equilibriums. The first one is where my cadmium, hexahydrate, reacts with an amine, a primary amine, methanamine. Right? Is it methanamine? Right? Yeah, methylamine. Okay, and that produces then that other complex plus water, and that's your stability equilibrium, or stability equilibrium for that one. Equilibrium 3, same, but now it reacts with the that 1,2-diamine ethane, and that's the En is shown in there. Okay, and again for waters. Those are the 2 equilibriums that are given. So an equilibrium is set up between the 2 complexes as shown in equilibrium 4. Okay, so now This is slightly different. This is now, if I look at my equilibrium 4, this is my reactant, and this is my product in there. Right? So let's quickly do the following. We need to rewrite these equations actually. So we need to turn the first equilibrium around. If we turn that around, you will see the following. That cancels out, and also that my waters cancel out. So if this becomes my reactants, and then these two, right, are my products actually that form in there. Right? So reactants over products, this is why we have what my products over reactants. So it's products over reactants. And remember that if we have that, that's my stability complex 3 over my stability complex 2. Okay, calculate the value of Gibbs free energy. Well, here we go, the same thing. What do we need to remember? Well, we need to convert my entropy again into kilojoules. It's in joules there, so that needed to be converted. Temperature is given, it's fine, and my enthalpy change is fine. I get a negative value. That's a 2 marks in there. State how the value of my Gibbs free energy changes as the temperature increase. Okay, so as my temperature increase, that value is negative. The T delta S is negative. It's going to increase and become more negative. Alright, that's how it's going to change. State how it's going to change. So don't ask what's the effect of it. Well, my value will become more negative and it will become more feasible. Define transition element, one or more stable ions with partially filled d orbitals. Really important in B that you know the theory for that. I'm happy you guys got the electronic configurations. You also got the 2 transition elements. Just be careful. I was perhaps a bit lenient. They ask for elements, not ions. So it's chromium and manganese. If you don't use the symbols, name, and they say name, that means you have to write out the 2 names of the elements, not the ions, not the symbols. Please do that. Cobalt plus 2 sulfate is added to water to form a pink solution containing complex P. An excess of concentrated hydrochloric acid is then added to the solution to form a blue solution containing your complex ion Q. Complete the diagram to show the 3-dimensional structure of Q. Okay, so it's cobalt, and we are going to exchange my water molecules with chloride ions. Okay, so remember your chloride is a larger ligand, so you can only fit 4 around it. So that's the maximum. Please remember the 3D structure from my tetrahedral. So 1 coming out, and there's actually 1 going back, and then 2 in the same plane. Cobalt has got a charge of plus 2, each chloride with negative 1, so my net charge is 2 negative. This is called ligand exchange. Ligand must be there, exchange. You can call it substitution as well if you want to. I won't go to the other options. There are possibilities, but rather stick to ligand exchange or substitution. A nice 4-mark question appears in almost every question. how you must explain why the solutions that contain transition element ions are often colored. Right, so you need to talk about your d orbitals splitting into two energy levels, your non-degenerate d orbitals forming two degenerate energy levels, d orbital energy levels. All right, as when light shines, it absorbs a specific frequency or light corresponding to the energy gap between the two d orbitals. Those electrons would then get excited or promoted to the higher d orbital, and what we see are all the other wavelengths that are not transmitted or reflected, or you can say the color seen is complementary to the color absorbed. So 4 marks in there. Why are the colors different? Well, because the energy gaps are different, which means different wavelengths would be absorbed in there. So NB, these two questions must pay attention to that. Right? Read through the memo, see those. And then, let's read through this last bit. A solution of a bidentate ligand 1,2-diaminoethane is added to an aqueous solution of cobalt sulfate. Oxygen is then bubbled into the mixture and form a complex with the formula that. Okay, the complex exists as a mixture of two isomers. The geometry, both isomers complexes are octahedral. Okay, so meaning if it's octahedral, there's 6 coordinate. The coordinate number is 6. At least we can know that. And say the reaction, cobalt undergoes 2 types of reactions. One type of reaction is the same as that is described as CI, so a ligand exchange. Right. The other type of reaction that cobalt undergoes is oxidation. Remember, this is why the oxygen is in there. All right. If the oxidation go in there, then it's oxidized. Please don't use the full structure of this diamine ethane. All right. So rather use these yellow structures. Right. Please also remember to use a nice structure. If this is my cobalt, this is how it should look like. So the square planar part is the 3D. It's the 2 going to the back and 2 going to the front. And now those are linked with the N. Alright, so N. There we go. So that gives me basically this structure in there. If we change it slightly, you would say it becomes optical isomers of each other. Guys, and that's the long and the short of it for drawing those structures. Please, it's not that difficult. You just need to practice it. Right, stability. The stability constants. Alright, there's some given in there. We know the more stable something is, the greater the stability constant is going to be, and the higher concentration it will be present in a mixture. So this is what I've just written down for myself. When I see a question, I write down what I know, and then I try and answer the question. So I think this is, in any case, your answer to the last I in there. And the expression for the constant stability. Stability constant, my goodness, my words failing me. There we go. So there's nothing weird on this. You guys got it. I'm happy. It went well. If there are any questions, please ask.